Okay. Hi, everyone. My name is Jonatan Pettersson, and I work as the technical sales manager at Modvion. And at Modvion, we're making net zero wind power possible. And as my predecessor stated, we do this by building wind turbine towers in wood. Our mission is that renewable energy should be built with renewable materials, and Modvion accelerates the transition to renewable energy and materials by building the wind turbine towers from laminated wood. So wind turbines are growing, not only in volume, but also in sheer size. So from 2021, the average turbine sizes are forecast to increase from 3.4 megawatts to 6.6 megawatts by the end of the decade. The average tower height will reach 160 to 170 meter and continue to 2027 and continue to increase thereafter. This is driven not only by the fact that the larger turbines and the larger rotor diameters require a taller height, but also that the taller turbines reach stronger and more stable winds and produce then cheaper energy. When reaching these taller heights, obviously there's going to be a limit in how the towers are going to grow in size, the diameters are going to be larger, or you're going to have to use significantly more material. And this is what we see as a challenge in onshore wind today. The wind turbines grow, the components grow, but the roads don't, which make transportation a very large challenge for the industry. Modvion has a solution to this challenge. We build modular and cost-efficient tall tower solutions for wind turbines. The towers are, due to its modular design, transportable. As they are made from laminated wood, they have a stronger weight, higher strength to weight ratio compared to its competitors, that's the steel or concrete towers, which makes it cost efficient to build, and it's also sustainable, as it has a net positive impact, as the carbon that is enclosed within the trees when they grow is kept inside the material for the lifetime of the product itself. So this makes it possible for us to reach the taller heights that the market are asking for. The wooden material is used to create circular cross-section towers, just like the ones that the industry are considering today. But instead of making them out of steel or concrete, for example, we use a material called LVL, which stands for laminated veneer lumber. Laminated veneer lumber is basically a form of advanced plywood, where very thin sheets of wooden fibers has been cut out, and they are stacked on top of each other and laminated together. The difference between plywood is that the LVL allows for the wooden fibers to be oriented in the desired direction. So for our application, that means that the majority of the wooden fibers are running in the parallel direction of the tower, which is in the direction where you have require the highest strength, basically. This also makes it very flexible in the perpendicular direction, which makes it bendable. So we have a custom layup. The material as such is used a lot in the construction industry, but we have a different layup compared to what they are considering. So this is a patented solution that we have. This tower wall is then the complete load-bearing system of the wind turbine tower. So today I was gonna walk you through the process of how to make a wind turbine tower made out of laminated wood, which is graphically outlined here on this slide. As you can see, the incoming material of the LVL sheets arrives at the factory as flat sheets. They are prepared and they are stacked on top of on our lamination machine, which basically is a mold that has the desired circular dimensions of the tower. So they are stacked on top of each other, and adhesive is applied in between each sheet. And when all the sheets has been stacked on top of each other to form the full thickness of the wall, hydraulic pressure is applied. The hydraulic pressure is kept constant until it has cured. And when it has cured, the pressure can be released. And due to the lamination and the stacking of these sheets on height, it has become very form stable. So it will retain its curvature even when releasing this pressure. And then we have created what we like to call our modules. So that's like one piece of the Lego puzzle it is to build our wind turbine towers. These modules are then moved to the next step of the manufacturing line, which is the machining cell. In the machining cell, we have dual robot arms that traverses along the length of the modules and also on the short side, or can reach the short side at least, and cuts the outer geometry of the modules to a very, very precise shape with very, very low tolerances. After the machining step, the modules are moved to a coating facility. So we have a weather protection system applied on the outside. Internals are mounted on the inside, etc., or prepared for internals at least. They are then ready to be transported to the site where the wind turbine is to be erected. And you can see here with the crane, they are erected to a vertical standing position and mounted to an assembly fixture, where they are constructed into what we call a section. And a section is basically a part of the tower that can be stacked on top of each other. So we stack all of these sections on top of each other to create the full wind turbine tower. And finally, the rotor nacelle assembly can be placed on top, and a complete wind turbine generator has been constructed. So to give you a bit of a better understanding of how this actually works and looks in real life, I have some pictures and actually videos here of the lamination in the factory to get a better understanding. So we see here that the flat sheets are moved onto the lamination module, while the lamination machine here traverses across each sheet to cover each layer basically. And when all of the sheets has been applied, the hydraulic pressure is applied. And then it's kept like this until the adhesive has cured. And then it retains this shape. We have a factory just outside of Gothenburg, where we have, for the current project, we have produced modules that are 15 meters long and weigh around 10 tons. The modules, however, can be produced in flexible width and length. So in the machining cell, the robot's arm that is seen in these pictures will cut a very precise geometric shape. They have a circular saw with a diameter of 900 to 1,100 millimeters. And these robots will traverse along the length of the module and will cut the outer shape with a precision of 0.2 millimeter over 15 meters length. So this is very, very high precision manufacturing for wooden products. The modules, when transported to site, comes in a horizontal configuration as seen here, and is then lifted to the vertical standing as seen here, and placed on this assembly fixture. So for the current project, we utilized 4 modules to comprise the full circular cross-section of the tower, but also this is flexible and can be adjusted to accommodate any transportation limits or that needs to be kept within some transportation constraints, basically. In order to keep this puzzle together and to retain this strength that is required from a wind turbine tower to withstand the full lifetime of cyclic loading, etc., there is obviously going to be large demands on whatever joints is keeping the modules and then sections together. So we have developed, there are 2 types of joints. We have what we call the longitudinal joints, which connects the modules to create the section. So the longitudinal joints connects the modules along the longitudinal edge. So like this, basically, is what we saw in the previous slide. So it's the in between each module here. And this is basically an adhesive butt joint. So we inject adhesive in the cavity that is formed between each module. This joint is of a very high strength. The main purpose of this joint is to carry the in-plane shear stresses, which is basically the torsion and twisting on the tower when subjected to any asymmetric loads from the rotor. In this direction, the joint is extremely strong and carries this very good. So the joint is actually stronger than the wooden material itself in this load direction. Then when stacking the sections on top of each other, we have what we call the transversal joint. The purpose of this joint is obviously to carry the loads between each section. This is done by a GIP solution, so a glued-in plates type of joint. So as we've seen in the previous slide, there is a slot pattern on the short ends of the modules. And this is matching on the meeting sections. So from the inside of the tower, perforated steel plates can be inserted into each slot. Adhesive can be injected into these slots. The adhesive will then fill all of the cavities. So that means that it will adhere to the wooden surface in each slot. And it will also create dowels in these perforated holes of the steel plate. So that means that the load is going to be transferred from the tower wall through adhesion to the adhesive, and then from the adhesive to the steel plate through mechanical interaction in these adhesive dowels. And here we can see the section stacking in action. One of the sections is lifted like this. We have a crew on top that is ready to receive the section and also to insert the steel plates from the inside and inject the adhesive required. So obviously there's a lot more to building a wind turbine tower out of wood than just what we've seen so far, which is obviously challenging. And that's to show that the design has the sufficient strength that is required for such a demanding application as a wind turbine generator is. The loads that is applied on the rotor is extreme, to say the least. So we have designed our tower in accordance to relevant standards. So that is both the Eurocode standard, which is traditionally the go-to standard for wooden constructions in the traditional construction industry. And we kind of merged this with the EIC standard, which is the general design standard of the wind turbine industry. This, as when making an innovation like this, the existing standards are not sufficient, obviously. So what we've done in addition is to carry out an extensive test program. So that's a test program of the materials itself and the joints that I just explained. And the tests were carried out both in static loading and in dynamic loading to make sure that the tower will withstand all of the dynamic loads that it will experience during the lifetime. And the testing was done in collaboration with RISE, the Research Institute of Sweden, to make sure that the testing was done in accordance to the applicable standards. And the testing and the design was then certified by a third-party body, in this case TÜV. So they have reviewed all of the test program, all of the design documentation, etc., to put their stamp on our documentation to state that we have made the sound engineering judgments, we have followed the applicable standards, and it is safe to erect this wind turbine tower, and it will be able to carry the loads for the full lifetime of the tower. Now it's stuck. Here we go. Okay, so all of this has ended up in our first commercial installation of a 105 meter tall tower, so that's the hub height of 105 meter. And this was erected, this is just finished this fall. The tower height itself is 103.3 meter with a base diameter of 5.65 meter. And this is actually the tallest wooden structure in the Nordic countries today. The turbine on top is a Vestas V90. It's a 2 megawatt with a rotor diameter of 90 meter. And this has been erected outside of Skara in Sweden. So now that we have shown that this can be done, we can actually erect a wooden wind turbine tower. We will take the knowledge that we have gathered and the experience, and we will continue to develop our concept, and we will develop this to be designed for the largest onshore platforms there is on the market today. So that's going into the 6 megawatt range of wind turbine generators, and also reaching the heights of 160 to 170 meters that I mentioned in the beginning. We will do this by considering relevant design upgrades to the structure itself, but also to optimize our manufacturing line and installation procedures to be able to produce these towers in volume and be ready to deliver in large volume scale from 2027 and onwards. And this was all I had to present today. I want to thank you for listening. I hope you found it interesting. And if you have any questions, you can just grab me, and I will try to answer the best I can. Yeah?
What big challenges is the company facing in the future to try to begin producing at mass scale? Yes, sorry. What issues or problems does the company see that they have to face to be able to achieve production at mass and scale? So we can go from one test tower to it being everywhere.
Yeah, obviously there's going to be, as our manufacturing facility for one is very limited for the time being. There's obviously going to be there's a lot of need for optimizing the entire manufacturing line to ensure that we can produce these volumes, and this is going to require significant investments. So we're going to need to invest in new machinery, and we're also going to have to invest in larger facilities to accommodate this manufacturing line to be able to reach these volumes that we are aiming to reach in order to make a sustainable impact for real within the industry.
Are there more towers to come within the next time?
Obviously, when doing this, there is challenges every day that needs to be overcome. There are technical challenges that we solve on a daily basis, whether it comes to the manufacturing, whether it comes to the design, the installation processes that needs to be very optimized. So that's what we do all day, every day, basically. And also, we need to convince the industry that this product will solve a lot of their challenges, and that we have a technology that is mature enough to be mature enough that they can buy it at a large volume scale as well. So there's a lot of convincing the industry that the way they have done it so far is not the only way it must be done. So that there are room for improvement, both in terms of, as we see it, technically superior solution that can reach the taller heights, that will increase production, but also that will make the industry more sustainable. And to move away from all of these carbon-intensive materials that is currently used, such as steel and concrete.
Thank you. Are there any competitors in this market? Are you the only ones doing this, or are there other people also trying it?
There are some. I mean, in general, there are other modular tower concepts that are our competitors. They mainly use steel or concrete. Then there are some smaller competitors, you can say, in the modular wooden wind turbine tower range. But the way we see it, we have definitely come the furthest at this point to accomplish this, our vision and goal.
And where will we see the next tower?
That's too early to say.
Okay. More questions?
What about the wings, the blades? Have you looked into that too?
The blades are interesting. We have we have had thoughts about the blades, but for the time being, we are focusing on the tower, which is the largest quantity of materials being used basically in the complete wind turbine generator. But this is something we keep in mind. We know there are other actors on the market that are looking into wooden blades as well. And this is something that could be interesting to look into more in detail for the future.
Good. Thank you.
Thank you.
Yeah, another questions? Okay, then. Thanks a lot for coming and this interesting insights.
Yeah.
Yeah, thank you.
Thank you. Thank you all for listening.